Okay, welcome. Okay, welcome to the afternoon session. Our first speaker is Natalia Berloff from Cambridge University, and she's going to speak about physics-based bifurcation computing.
Yes, thank you. Yes, thank you. I'm from Cambridge, and I have to apologize for myself and for my Cambridge colleagues, because this is absolutely the worst week to have the conference. We're all at admission interviews. So fresh from this mind-boggling exercise of selecting the best undergraduate students. So from 8:30 in the morning to 7 in the evening. So I'm very sorry that I missed this amazing workshop, but I'm so happy to see so many familiar faces. Also, so I'm going to speak about physics-based computing, and the title seemed to be odd for this kind of conference. But actually, as you very quickly see, what I have in mind is how the wave system, the system that is capable of pattern forming, with the waves propagating, splashing, and creating some particular states, can be used to do an analog computing. So, and that will be the subject of my talk. And I will focus on a particular system, the system of exciton polaritons. But then I'll take it further and will show how the principles by which the system operates can actually be applied to solve problems. So I would like to actually start. It switched here. It didn't switch. OK. I would like to start, first of all, by thanking my group. So the research actually on this more physics computing started with Kirill Kalinin and Nikita Stroev. So Kirill is now with Microsoft, the resident there, and Nikita is postdoc at Weizmann Institute. And my current group of brilliant PhD students, James, Marvin, Richard, and Irat. And I also would like to thank the groups in Microsoft. This is Optics for Cloud group, and Francesca, Christos, and Hitesh are group leaders. OK, so my outlook for the talk is I'm going to give you the example of polariton condensates. That would be the topic. So we'll form the lattices and we'll arrange the condensates in such a way that a particular problem is solved. So I'll talk about lattices, about problems with computing, and that would be the focus on the focus of my talk. But I would like to bring you into attention the actual computer that is about to be built and become publicly available. So this is from our collaboration with Microsoft, where we implemented the principles of what I'm going to talk about in the actual optical hardware, complemented with a digital large-scale simulator that uses these principles. And please email us to get the free educational access to solve optimization problems. So it will be launched early next year. The all optical will operate with 50 variables, and we also have the state-of-the-art package for solving optimization problems on a large scale, thousands elements. OK, so one quick slide. So actually, the computing started with analog computer when electrical circuitry has been used to actually simulate the differential equations. They describe the work of electrical circuits. But of course, the world has changed with an advent of the digital computer based on von Neumann architecture, which then followed by this very intriguing and fascinating idea of using quantum computers to represent quantum gates, exploit entanglement, or perhaps quantum tunneling. But now I think in the last roughly 10 to 7 years, an alternative path has emerged, revisiting the idea of using the analog computing. So now with the tremendous advantages in being able to control and operate various physical systems, now we can revisit this concept and build instead of trying to build the universal computing, to build an application-specific architectures that are aiming at solving a particular type of the problems. And in doing so, we use the analog operation of this natural physical system. So what does the physical system actually do to reach a particular state, let's say ground state? And on this route, we use, of course, parallelism, that many processes occur in the system simultaneously. If we have optical or other low energy consuming devices, that we can expect that they will be extremely energy efficient, etc. So we hope that this analog operation of the natural physical system is actually the next step in solving specialized problems. And here I would like to give you one example. So what you would see, this is an experimental image. What happens here occurs on a time scale of 100 picoseconds. So very fast operation. You'll see the momentum space and the real space of the lattice of 100 polariton condensates. So on the matter of 100 picosecond, you will see how the system solves 3 different hard problems, actually. So as we start, we created the condensates, and then the coherence takes place. Oops, no, sorry, how to stop it? Okay, I won't stop it. So you will see that it solves the problem when the coherence across the lattice site is established, and all connections are in phase, so ferromagnetic interactions, and then the problem rearranged itself with a different coupling between the sites. Then you see antiferromagnetic coupling, and again, everything is destroyed, the different intensity, and the problem is solved for the 3rd time with again, antiferromagnetic couplings. But this problem, so that's what we expect from the physical system. Very fast, in analog fashion, a hard problem is solved. But now let's ask, so what kind of question we can expect to solve on this hardware? Of course, what you've just seen, very impressive, but it's not a very useful problem to solve because you are not controlling the individual couplings between the elements. Okay. In practice, we deal with optimization problems. And this is a mathematically rigorous statement that usually all optimization problems, even NP-hard optimization problems, can be mapped onto minimizing of universal spin Hamiltonians, classical Ising Hamiltonian, classical XY, K-local, pots, etc. And you can do it with a polynomial overhead. So you're going to change the number of variables, but not dramatically, as a polynomial, not exponentially. So you start with your favorite problem in mind. You write it down as the graph problem, the problem living on the graph, where each node has 1 or more variables associated with it. And then you have some coupling strength that connects the element on this graph. And then the problem of minimization actually will be formulated as the problem of finding the relationship between the variables so that some spin Hamiltonian is minimized. So again, if I start with the function f that has k variables, I'm trying to find the lowest lying state, the lowest energy state. I map these variables onto, let's say, phases of the variables, and then I'll have n of those. Again, the growth is only polynomial. And then the structure of this function will be mapped onto the couplings between these variables. So the entire structure of the function that I'm optimizing is contained in this coupling strength that represents the connection between the ith variable and jth variable. And then you can have the cosine of the difference of the phases. In this case, you'll have an xy minimization, or these thetas can be discrete, 0 and pi. Then this is the classical Ising Hamiltonian, or you can have more than 2 states, and then you have pots or clock Hamiltonian to minimize. Okay, and so along these lines, in the last, again, 8 years, a lot of platforms have been proposed and explored with the goal of using this procedure of mapping into universal spin Hamiltonian and then use the natural operation of the physical system to actually solve or minimize this Hamiltonian. And of course, the work starts with the seminal work by Yoshi Yamamoto, coherent Ising machine, based on optical parametric oscillators. Near Davidson with his laser in a cavity. There are injection-locked multi-core lasers. There are optoelectronic systems photonic lattices, memristors, and we contributed to this research with our polariton graph simulator that I'm going to talk about. Also, Claudio Conti with his spatial light modulator-based machine. Okay, so let me talk about the principles of the system. So actually, I can think of two types of the system. One is optical, and one is a matter wave system, or conservative system, or dissipative, but the system that has the proper defined ground state. So for the optical, I think of the gain dissipative systems, such as lasers, optical parametric oscillators, polariton, photon condensates, magnon condensates. So all these systems that would not exist without a drive. So if you turn the laser off, the laser is off, so there is no coherence at all. However, in a lattice system that consists of matter waves, such as atomic condensates and optical lattices, spin liquids, etc., actually, if there is no gain, the system is still there because it consists of the matter particles. In this optical system, the couplings usually are dissipative because the system itself, the optical system, operates by minimizing the gain. So as you increase the pump in optical system, you create the source of the photons, excitations, and then the coherence is formed when there are enough quasi-particles or photons in the system. In other words, when in the states that minimizes the losses. So this is the main source of the operation. So the couplings between the elements would be of dissipative type. Whereas in a matter system, it comes from the kinetic energy, and so the couplings usually of the dispersive type, the Josephson type of coupling. But in both systems, the answer is red. The answer to the problem is when the coherence is established, and this is wave coherence. So in these systems, again, there is no proper Hamiltonian. It's non-Hermitian system. So the system minimizes losses. It doesn't have the Hamiltonian. But as you formulate the loss profile, this is the function that you would like to map your optimization problem into the loss profile. And then you would like to, therefore, bring the gain, so that if this is the loss profile for the system, I increase the gain, and then hopefully the first mode that lasers, the super mode emerges that correspond to the first state that minimizes these losses. And so by doing that, I have the state of the system, which is in the global minimum of this loss potential. For the lattice system, on the other hand, as you cool down the system relaxes, and if you guide it properly, then it may end up at the ground state, or it may get stuck at some local minimum. So the question is how to actually anneal it so that it actually goes to the ground state. For this system, another characteristic is that you have bifurcation from vacuum or from the threshold. So the typical situation is that you don't have any well-defined spins until the gain exceeds some critical value. Then you have the Hopf bifurcation, and then you can associate the phases 0 and pi with the solution of the problem. Another interesting feature of this system is that actually the gain profile depends on the occupation of the wave numbers, or the wave amplitudes. And so the system propagates and reaches this minimum losses or the ground state in ever-varying energy landscape that actually also helps the annealing to take place. Okay. So let me give you maybe the last slide before I go to polariton system. So the critical ideas behind the success in using the system for the minimization, for finding the low energy state, is this is actually a dynamical system that has the gradient descent built into the structure of the system. There is the coherence, synchronization. So if we think about it, it's a quantum system that we usually deal with. But so before the condensation actually occurs, we have the quantum system with entanglement with a large span of the Hilbert space. But when the synchronization took place, that's when the system becomes coherent, very analogous to measurement in a quantum system. We have this mechanism for actually choosing the state that corresponds to the ground state in mode selection or thermalization if we have matter wave. assisting is this bifurcation from vacuum at the threshold and the amplitude-dependent coupling strength. So just to give you again this idea, let's suppose that this is the landscape that we minimize. It's actually the actual landscape when we projected everything on just remaining just a single parameter theta. The global minimum would correspond to this 4 pi over 5. However, if you start in this potential, then you quickly follow the gradient descent and would end up in the local minimum. However, if we have this system where the landscape is varying, you start at the same point, but at this moment, this is the landscape. So you follow the gradient descent. At the next step, again, the landscape has changed, but you follow the gradient descent, it changed again, approaching the true loss landscape, but at the end, you will follow the gradient descent and you will end up at the correct global minimum. That's what this annealing, and that's the dependence on the structure of the function on the occupation really becomes important. Okay, so let me talk about polariton condensates. The time is kind of... Okay, so polariton is a quasi-particle, the hybridization between photon and exciton. They exist in semiconductor microcavities. So think about the laser exciting the electron, so creating an exciton, so electron-hole pair, which is unstable. It spits out the photon, and if the mirrors, the Bragg reflectors are placed, the photon gets reflected, excites exactly the same exciton, and we have superposition of states. It's not like exciton or photon. It's a superposition called polariton. So polariton are bosons, so they undergo Bose-Einstein condensation. And because being part light, part matter, the effective mass is actually very low. It's 5 orders of magnitude lower than mass of the electron. So they're very light. The temperature for the Bose-Einstein condensation is inversely proportional to the mass. So low mass means that we can actually achieve the condensation of these quasi-particles at the relative warmth of cryogenic temperatures. In the experiments I'm going to talk about, it's about 10 Kelvin. However, you can also have some polymers and achieve the condensation at room temperature. So again, important if you're trying to build the computer with it. After bouncing back and forth between the mirrors, for photon, exciton, photon, photons leak through. So they have a rather short lifetime that can vary depending on the thickness of the mirrors, on the quality factor. And you can vary, therefore, from few picoseconds to 100 picoseconds. It's again dissipative system. If the laser is off, there are no quasi-particles. But because of the structure of the sample, of the lifetime, of the mass, you can actually fill in the gap between equilibrium and non-equilibrium systems. Also, you can vary the strength of the nonlinear interactions in the system. They're possible at room temperature. And therefore, there is a lot of parameter in the system that you can actually change. Okay, one slide maybe on the modeling of this system. The usual model invokes the Ginsburg Landau equation because of Gross-Pitayevsky with gain and dissipation. So this is the equation that familiar to this audience very well. So in the condensate, we have the usual kinetic energy, the dispersion, diffusion. Because of the interaction with a reservoir of hot excitons. We have interactions between polaritons. We have the blue shift polariton-exciton interaction, so interaction with the reservoir. Then we have scattering from the reservoir of hot excitons condensing into the polaritons. We have the linear losses because of the imperfection in the structure. And also, importantly, we can combine resonant and non-resonant pumping. So in this case, we can have a pumping with, and here is the resonance with the condensate. For the reservoir, we usually take the simple rate equation. When you have incoherent pump, the dissipation of the reservoir, and again, scattering into the condensate. If I assume that the relaxation of the reservoir is fast, then I can assume that this is 0, and therefore the density of the reservoir is simply the incoherent pump divided by this expression. And expanding in Taylor, assuming the small densities, gives me the standard Ginsburg Landau equation, perhaps in a little regime of the parameters that has not usually been studied. Notice that also if I substitute this expression into the original equation and combine, I can see the nonlinearity actually can change the sign as I increase the pump. So usually we have defocusing interactions, but as I increase the pump, this can become negative, and then the condensate enters the attractive regime of the attractive interactions. Okay, to build a computer, you need to build the lattice. And so that started to work in collaboration with, it was our theoretical prediction with Jonathan Keeling, and then we followed with help from Jeremy Baumberg and his group. When the condensates are pumped, in this particular case, at the corners of equilateral triangle, and establish this lattice of vortices, positive or negative winding. But what was very interesting, what emerged from this experiment, is actually you can put these condensates very far apart from each other. Nevertheless, they arrange and they have the fixed phase difference. So we explored this further. Oops. Yep. So that was the first question, how the condensates actually know what phase difference to establish when the characteristic width of the condensate is about 2 microns and you place them on large distances of hundreds of microns. Okay. But also, we explained this, the phase difference that the condensates try to establish, again, by the principle of the minimum loss. So in this platform, if I have the system of n-coupled oscillators, and I'm trying to see when the loss of the state in the coherent state is minimized, I'm looking at the question of when the total number of particles is maximized. And so if I approximate, this is like zero-order approximation, if I approximate these condensates by the sum of the individual isolated condensates, then and expand this, so I have something that does not depend on the relative phase, and then I have the term that depends on the relative phase between them, and that gives rise to the XY model minimization. Okay, and so after that we went quite a path shown by this error. So we, with Jeremy again, a lot of questions concerning the lattice were addressed, in particular again, so we noticed that the coupling can be established on staggering distances of 100 to 150 microns, whereas the single condensate width is just a couple of microns. With Pavlos Lagodakis at Southampton, we looked more closely at how the system establishes this phase difference and showed that it depends on the distance between the condensates as well as the outflow wave number, on the velocity with which the condensates flow from the position where they were created. And the coupling strength, therefore, can vary. It's kind of a Bessel function. It can take positive ferromagnetic and negative antiferromagnetic interactions, and you can change the strength between them. With Jacqueline Bloch and Alberto Amo, we came up with a scheme of how to establish the long-range couplings. Because with geometry, you can play as much as geometry allows you, right? With 3, you can have arbitrary 3 connections. Already putting the 4th condensate, requires something else. So the answer to that was that we can use the fact that the condensates actually emit light and collect this light. Remember, the photons get flown through the mirrors. So you can take these photons and redirect into a different remote condensate, and that creates the coupling between the condensates. But then to do that, you need to have a sufficiently long coherence of light. So you have long-range couplings, you have to have long lifetime. And so this is now work in progress with David Snoke in Pittsburgh. So one more slide on realization of the actual XY model. Again, this is experimental image. This is what we expect from XY. And this is what theory, the full numerical simulation of the governing equations, gave us in full agreement with what we expect from the XY minimization. So this is really what the system does. This is more recent work where we built something like analogous to the Dwave machine, perhaps. So if you take if you create the condensates at the corners of a pentagon, then depending on the distance between them, here you have antiferromagnetic couplings between the neighbors, but no couplings across. And the system establishes the phase difference between adjacent condensates as expected from the XY model, 4 pi over 5. However, if you change this lattice constant, if you bring them closer, now they also start interacting with the neighbors, also antiferromagnetically, and the interaction stronger than with the nearest neighbors. And then the phase difference that the system has is, again, it's 2 pi over 5. Again, that's what expected from the XY model minimization. Okay, I have 2 more slides. So we can exploit this physical mechanism behind the operation of the system and see if we have this kind of physics-inspired digital method. So we can program the operation and put there all the necessary ingredients for the minimization of the XY Hamiltonian. So if I'll do tight binding approximation on a full Ginsburg Landau equation with a reservoir, then we have kind of Stewart-Landau equation. So now I suppressed all the spatial degrees of freedom. Now the order parameter that describes each condensate depends on time. It has amplitude and phase. And then we have the rate of change of psi is given by the injection, the rate at which we inject the particles in the system, the linear dissipation, the separable nonlinearity, self-interactions, and the coupling between the elements, and perhaps the noise. If we look at the fixed points, we'll see that indeed we have kind of an XY minimization. However, the couplings between the elements are modified by the amplitudes. And you don't know these amplitudes before the fixed point is found. And also, if we look at the dynamics of the phases, again, we have something that is very similar to the gradient of the XY Hamiltonian. However, again, these couplings are modified. So that suggests that we need to bring all this amplitude to the same value. So we need to put the injection feedback where each of these injections now individually modified so that all the amplitudes go to the same value. Just put one here. And so with this feedback mechanism, now we do have minimization again of the XY, because if I now count the total mass, every amplitude is 1. So in the system of n condensates, we have mass n. We have the total injection, the total power we put in our system, the total loss, and then we have this XY model. So this is fixed, this is fixed. This is we control to take the minimum value. We just put as little power as possible. And that gives us, therefore, the minimum of the XY Hamiltonian. And then we actually, so that works very well for the XY minimization. This is the little simulation just to illustrate how all the densities are brought to the same value, 1. 50, okay, that's scaled. All the phases also establish themselves according to the XY model. And here we compared this with just randomly generated matrices of coupling matrices using Monte Carlo and the local solver to find the minimum. And in blue, we show the result of running these networks on these matrices. And notice that we do very well for all the matrices except perhaps for these few. But for these matrices, we notice that occurs when the spectral gap, the difference between global and excited state, is very low. So our system can actually mistake the ground state for the first excited state if they're very, very closely spaced. Okay, but otherwise, it's really a very good method. The one before the last one. So after that, actually, there are quite a few modifications that we looked into. in particular combining non-resonant pump to simulate Ising model, using the fact that we know what the parameter that we need to control and keep at the minimum, the role of the nonlinearity, the change, how the complex type of the coupling actually can help generalize it to k-local Hamiltonians, etc. And for my conclusions, this is new and rather excited field that actually combines quite a lot ideas from the various fields. Especially, we look very closely now into excitation and dynamics of the non-equilibrium systems, because these excitations on a glassy profile, actually glassy Hamiltonian, actually prevent us from finding the global minimum. And on this diagram, so we, in the hardness of the problems, we have this usual easy, hard, easy transition. And we hope that this unconventional computing, this physics-based computing, actually can help to solve some hard problems that otherwise are not suitable for other methods. Okay, thank you.
Thank you very much. Thank you. Are there any questions for the speaker, Pavel?
No, madam. Okay, so question. So you showed this time scale in picoseconds, right, for lifetime. Is that your analog computer will work on a scale of picoseconds? What will be?
It depends. It depends. So for, I mentioned Microsoft one. It's a different system. It's an optical system, but more kind of classical optics, and where the iterative part, the electric circuitry, actually represents the model that I suggested, right, that I explained. So there, the speed comes, we expect the calculation give us about 2 orders of magnitude improvement over the existing GPU on the size of from 1 to 2,000 variables. With this system, again, you need to do, with the polaritons, you have picosecond operation, but you need to do the feedback. Feedback takes, microseconds, and you need to do it several times throughout. So that also, some estimates show that potentially we can do better than classical computers starting from 1,000 variables as well. And then the behavior would also be exponential, but not as steep as for the classical computer. Don't take me wrong. We are talking about NP-hard problems. They cannot be solved in polynomial time. The time will still be exponential. But what we hope to do is, for the limited resources, for low energy consumption, to give better solution faster. That's the task, not changing the actual scaling of the problem. That's impossible. Lincoln?
Thank you for your excellent talk. You started with a discussion of quantum computing, and then you...
Could you please speak up, sorry?
Yes. You started with a discussion... Thank you for your excellent talk. You started with a discussion of quantum computing and an adiabatic approach to computing, and then you moved into a semi-classical discussion and did classical many-body physics. Can you help me connect to your concepts of quantum advantage in this system? Is there some place where you make some predictions about entanglement or scaling or anything? Yeah.
That's a very good question. So first, you can think about the Microsoft machine is classical, full stop. We not even assume that there is anything quantum in it. It's classical. It's classical optics with electronic feedback, but it implements the schematics that actually was motivated by physics. Okay, so it implements the iterative process that comes from a particular system of differential equation that's pretty good in classically finding a good quality solution. For other systems, such as polaritons, that undergo there is this process of condensation taking place. When the condensation occurs, so when the condensates are formed and created a particular phase difference between them, when condensate is formed, that's, again, the system became classical. But what is important is the route by which the system finds this classical solution. So this is quantum statistics. The process of the Bose-Einstein condensation is governed by by quantum statistics. So here we expect that probably, but again, I don't have any proofs for that, we hope that the quantum character of these particles actually allows the system to span larger space, larger domain, before the condensation actually occurs. Whether or not it's true, I don't know. There is a hope in there, but that's but even with that, you see, what works for you is a parallel operation. A lot of processes occurs very fast and low energy consumption.
So Natasha, thanks on my end as well. So a quick question. You mentioned that as you turn up the power, your two-component system becoming a one-component system, you can actually make it attractive. So have you or other people leveraged the attractive nature of that to probe what happens in that case for your relative phases, for potential collapse and other issues?
Yes, also very good question. So the role of nonlinearity, you can choose the best parameter for each particular problem. The problem with actually answering this question precisely lies in the fact that depending on the structure of the problem you're trying to solve, you will have your own optimal nonlinearity, but it changes from problem to problem. But this is extremely interesting because it means that by perhaps finding some characteristics of this coupling matrix, because everything is governed by this coupling matrix Jij. So if you should be able to find a characteristic that tell you what is the optimal value for nonlinearity. Right now we know that yes, for some problems it helps. Even more so, another scheme that we consider is when this nonlinearity actually also, we can change nonlinearity and we can have a feedback in such a way that nonlinearity depends on the pumping strength. In this case, we actually can do so much better by allowing phases, because what nonlinearity does, it rotates the phases fast. If it rotates fast and you change the speed, then you can actually let system to find the configuration which is the best.
Excuse
Again,
me,
spanning larger.
Could the next
space.
speaker come? Oh, that's you, I see, okay. Keep going.
Yes, I keep going. Yes.
Okay, yeah, okay, yeah. So while we change, you can still...
Yes. So really, this nonlinearity is untapped resource. It is very good. It can be controllable in these systems, in many systems, not just exciton, polariton, condensate. And if you can establish the feedback with so that your pump depends on the nonlinearity, you can actually bring your system to find a better solution and faster. Because again, you allow phases to rotate, so you can span a larger space. So because you need to be in the basin of attraction for your global minimum. So it really helps. Okay.
Okay, thank you very much. Let's thank the speaker again. Thank you very much.
Yes. Oh, I should. Yeah.
You have your laptop.
Yes, my laptop. I should better take it, and I need to give the microphone. I exchange my laptop for your microphone. Yes, that's good. Wait.
Thank you. Remove that. Just like I don't get your hair.
Okay, so our next speaker is
in.
Quentin Glorieux. Yes, and,
Good job.
Talking about out of equilibrium physics in paraxial fluids of light.